Okay, good afternoon, everyone. We lost about 6, 7 minutes. Let's see. Let's pick up from where we left off last class, which was the timing diagram for the SR flip-flop. SR flip-flop. Let's switch over to the class notebook. Okay, so I did this timing diagram based on this SR flip-flop built out of two NOR gates. Okay, built out of two NOR gates. Any questions on how this timing diagram works? Did I cover this or not? Oh, I haven't. Okay. Well then. Okay, so SR flip-flop. Any questions about the operation? All right. So Qn is basically the current state. Qn is the previous state. Qn plus 1 means the next state. So, well, it simply means if my current value of the bit is 0, then Qn is 0. Previously, it may have been 1 or it may have been 0. So Qn minus 1 just means like previous, what the value of the bit was previous. So state is basically the value of that bit, or that signal. Yeah, and it can only take two values, 0 or 1. So a Qn minus 1 simply refers to the previous value of that signal. Okay, previous value of that signal, of that bit. Now here we have NOR gates, right, to build our SR flip-flop. Instead of using the NOR gate, you can also use a NAND gate to build it. Okay, so similar structure. You have two gates. I won't go over the entire operation, but I'll just draw it out and explain briefly. So we have two NAND gates. And again, same thing. We apply feedback from the output of one to the input of the other gate. So the circuit diagram is exactly the same. The only difference is, if you see the NOR gate here, R is connected to the gate that gives you output Q. Here it is S, or reset. Right? A NAND gate is a AND gate mated with a NOT. The truth table of a NAND gate, I mean, it's there in the previous slide, but I'll write it out here. What is it? Does anyone remember? Even if you don't remember, you should be able to figure it out. It's NOT of AND. 0 and 0 gives us 0, and then NAND would give us 1. And same thing with zeros and ones and zeros. And the only input for which it goes low is when both inputs are high. Right? The only reason where it goes low would be when both inputs are high. And so using the same techniques that I used to analyze the NOR gate flip-flop or NOR gate SR flip-flop, you can use the same techniques by applying 0 and 1 state for S and R and computing Q and Q naught. Okay, Q and Q naught. So it is possible to create it using NAND gates or NOR gates. The truth table still remains the same. SR flip-flop still has a undetermined output when both inputs go high. Okay, that's why it says not allowed. When you have both inputs as high, if both inputs are high, if R is high and S is high, we don't know what state Q or Q naught would be. There's no predicting what that machine would do. Q could go 0, Q could go 1. And that's why it says not allowed. So when the circuit is being designed, this is of course a fundamental building block to explain higher order circuits. You know, SR flip-flop by itself is not going to be used. But when they first designed the SR flip-flop, designers take care never to set both inputs high at the same time for that SR flip-flop. Okay. So based on this flip-flop, we can predict what the output can be, or we can design what the output would be based on the truth table. And in terms of the clock inputs for both S and R, the set and reset inputs, we can graphically describe what the output would be. And that graphical description is known as the timing diagram. The reason we say it's a timing diagram is because, again, for digital input signals, everything is either clocked, or if not clocked, is controlled with a pulse of digital signal. So it has a fixed width. In this case, a 1 unit or 1 unit of time. Let's just say it was seconds. In reality, it would be milliseconds or microseconds or even smaller, right? If you have a clock that's running at 2 gigahertz, then 1 unit of time is going to be 1 over 1 gigahertz. So anyway, let's just assume that this was seconds. It's a very long period of time. And we break down the signal. So here it'll be 3, 4, 5, and 6. 5 and 6. And here we can see for time periods 1 and 2, the set signal or S input is high. It is low for all the others, high again, and then low and high again. And the R input, we break it down, 0, 0, 0, 1, 0, 1, and then you have 0 all the way through, and then beyond 11, it's 1. Here beyond 10, it's 1. So they work, the way the timing diagram works is basically you take a look at all the inputs, right? And then you look at the truth table. So what is the input for the first time period? S is 1, R is equal to 0. So what should be the output? Absolutely. So you go back, look at the truth table, and when S is equal to 1 and R is equal to 0, output is 1. When S is equal to 0, R is equal to 1, output is 0. Hence set reset. Remember, set stands for setting the output high. Reset means just resetting it to 0. In the next few slides, we'll also see another term known as preset. Preset also means high or logic 1. So set and reset, meaning when set goes high, output goes high. So if I was to draw the output, let's draw it right underneath. T, then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11. Right. So the timing diagram again for any logic circuit would work the exact same way. Timing diagram, we're going to take the inputs and predict what the output is based off of the truth table. So before I draw it out, the first 2 clock cycles of the first 2 states is going to be 1, right? So 1 here, 1 here. Then the third clock cycle, not third clock cycle, third cycle, both inputs are 0. What happens when both inputs are 0? It stays the previous state. So Jonathan, here's the example. At 2, between 2 and 3, we want to find what the output is. Input is 0, 0. Output is what the previous state was. Previous state means what it was before 2. and before 2 it was 1, and so output stays at 1. So previous state is another way of saying that the output will remain the same. If the value of the output is going to be the same as the previous state, it means it is not changing, meaning it's going to remain the same as the previous output. Yes. So 0 and 0. So here. So this and this are the inputs, right? S input and R input. And then we just take each, so we each time period, each time period we say, we look at what S and R values are. We take a look at the truth table, and then we look at what the output is. And so on and so forth. We can find the timing diagram for the rest of the time all the way up to 11. So if you now look, R is 1 between 3 and 4. If R is 1, output goes low, 0. And so between 3 and 4, output goes to 0. 4 and 5 again is 0, 0, previous state. Output remains 0. Next input, again, R is 1. If R is 1, output again remains at 0. So here, let me write down, this is Q n minus 1, where n is equal to 3, so the state is Q2, what the output was at Q2. Does that make sense? Yes.
It only applies for this case with the flip-flop or
no, like Qn minus 1, Qn plus 1. That's
no, it's format of it because we according to the table that we last time. So it's only applicable for this setup, no?
What is applicable? Yeah. The timing diagram, or
yeah, like the
yeah, this timing diagram is based on the SR flip-flop. Yeah. So it only applies to the SR flip-flop. Yeah. Yeah, it's only for SR flip-flop. The example is only for SR flip-flop. Let's see, where was I? So going all the way up to 7, the output doesn't change, right? It stays at 0, 0, 0, 0. Reset is 1. Reset is 1 here. Here it's previous state. Here also remains at previous state. Both of these time periods 5 and 7, where input R and S are both zeros, output is the previous state, but the previous state for both R was equal to 1, and so output stays 0 all the way up to 7. When we get up to 7, S goes to high. If S goes to high, output also goes high. And so at 7, output goes high. Between 8 and 9, output is previous state, meaning it remains high. Between 9 and 10, again, it is high, or S is high. So output is again high. And then after 10, it's 0, 0. So again, it remains at previous state. So all the way until 11, it remains high. And after 11, R goes to 1. When reset is high, output goes 0. And so everything else after 11, it is 0. Here again, this is Qn minus 1, Qn minus 1. Same thing, let's see, between 8 and 9, Qn minus 1, Qn minus 1. Does that make sense? That's how you would draw the timing diagram for any logic circuit. You would take a look at the inputs, then determine what the value is for those inputs for each particular time period. Take a look at the truth table and then predict the output. Yes.
Is it why when R is 1 and S is 0, isn't that 1?
Where? Which time period? For 9 to 10, S is 1 and R is 0. S is 1 and R is 0. Yeah. Yes, Mark. Yeah. Well, no, it's going into the RS. Oh, you mean like the values? Yeah, this is just arbitrary. Yeah, it's just, it's like an example to show timing diagram. It's like if you take a circuit analysis problem and you say voltage source is 5.7 volts, now find the current through the circuit. So it's like that. Yes.
How it's going to look like that output, like in the full circuit?
And the full circuit.
Yeah.
What kind of full circuit?
Like SR flip-flop, circuit analysis.
I mean, you get plus 5 volts, 0 volts, plus 5 volts, 0 volts, plus 5 volts, 0 volts. That's all you would get. You have to remember, so all of these digital circuits, you will use a transistor as a switch. So when it goes plus 5 volts, well, depending on how it's configured, you're operating the transistor between saturation, cutoff, saturation, cutoff, saturation, cutoff. So 0 current, max current, 0 current, max current. And so depending on how you're configuring the circuit, that's how it would. Depends on what you're using the circuit for. Yeah, but any circuit, any logic circuit, this is how you would determine the timing diagram, which is something like, if you're taking the labs, some students are taking the labs, you have already had some experience with timing diagrams. All right, any other questions? So notice that, I kept talking about clock inputs, clock, right? It's not synchronized. And so we have what is known as a clock input signal to synchronize both gates at the same time. The more important reason for a clock is to actually synchronize the entire system to one signal. We want everything to work in synchronicity, right? So when you have a clock signal present, that clock signal determines when a gate is going to turn on and when it's going to turn off, or basically when the gate is going to operate. Okay, so the clock signal basically synchronizes everything. So if the output of the circuit or the operation of the circuit depends on the clock, then we say it is a synchronous circuit. Okay, synchronous circuit. So if it depends on the clock, everything is synchronized to the clock signal. And we say it is a synchronous circuit. If there is no clock, then we say it is asynchronous. Attending the lecture in person or on Zoom during class time at 1 p.m. is synchronous. If you view the lecture video outside of class time, which is outside of 1 to 2 p.m., it's asynchronous. So digital circuits, same thing. If everything is along with the clock input, then it is called a synchronous circuit. Otherwise, it's asynchronous. Yes. Circuits gone nuts. We'll talk about it. It's basically the not allowed state or don't care state, meaning when, well, since you asked the question, let's begin there. So the question being asked was, what are the X's? What are the X's in the truth table? No, X's means don't care. X's means don't care. And the reason is, if you look at the circuit, we have two AND gates in front of the two NOR gates. So AND gate, 0, 0, output is 0. 0, 1, output 0. 1, 0, output is 0. The only case when the output is 1, if it's both inputs are high or both inputs are 1. So if you have an AND gate here, doesn't matter what value R or S takes, as long as C is 0, nothing is going through. And hence, when C is 0, when the clock input is 0, or where there is no clock, it doesn't matter what R and S is. The output is going to remain at the previous state, whatever the previous value was. That's different. We'll take, we'll talk about that afterwards. But as long as clock is 0, so 2 operations when you have a clock signal. As long as clock is 0, doesn't matter what the inputs are, output doesn't change. Okay, so that's one big separation. The operation of the circuit depends on when the clock signal goes high. So the clock is enabled, that's when the circuit will operate. So that's when the circuit will operate normally. So when it's 0, doesn't matter what R and S is, output is unchanged. Output doesn't change. So it's Qn minus 1. You could have 4 different inputs here, 0, 0, 0, 1, 1, 0, 1, 1, but doesn't really matter. Does that make sense to everyone? Right? If clock is 0, everything is kind of disabled. Output remains unchanged. Now, if clock is 1, well, then the rest of the matters. The first one, where both inputs are 0, R and S are 0, are going into the AND gate. So if clock is 0 or clock is 1, it does not matter. Again, the AND gate outputs, there's nothing at the output, it's just basically 0. And so this remains at the previous state, and hence Qn minus 1 again, when the input is 0, 0, which is what we have for a regular SR flip-flop, right? So the only thing the clock is doing is enabling or controlling when the output will change. Other than that control, the SR flip-flop operation remains the same. Just as a refresher, let's go back 2 slides. 0, 0, previous state. S is 1, output is 1. S is 0, output is 0. Right? You go here. Inputs are 0, 0. Output is previous state, Qn minus 1. S is 1, output is 1. R is 1, output is 0. The only thing the clock affects is basically the operation, meaning when the clock is enabled, that's only when the output will actually work. That's it. If it's 0, then there is no output. It remains at previous state, no change. So that's the only thing it is doing. And that's the point of that truth table, showing that the clock is not affecting the operation of the SR flip-flop. It is only affecting when it will actually work. So in the absence of a clock, the circuit's not going to work. It will only work if the clock is present. And that's it. That's the only thing. Let's take a 10-second pause. Think over it. Let me know if you have any questions. Yes.
So you know what was the clock? Is that special? Is that device, the extra that is attached to them? The clock.
The clock.
Yeah, is the device attached to it,
Oh, it's a circuit. It's an oscillator circuit that generates a frequency signal. Yeah, it's an oscillator circuit. Yes.
Also talking about this one, so you can generate 2 bytes from this.
Well, the output's only Q, so it's a 1 single bit. At the same time, we are able to get Q naught, but it's not a separate bit. We don't consider it a separate bit. It's only 1 bit. It's Q. So that's why the symbol Q. It's 1 bit. Yes. Like Qn minus 1, we are just signifying that the output has not changed. Because Qn minus 1 simply tells us the output right now is what it was previously. And there's no new information, it's just the same thing. So it's kind of like so in memory storage applications, that's where we would use that. Yes, Marco. Oh. Well, yeah, you can, yeah, it's fine, go. Q naught is just Q bar is Q naught, the opposite of Q. So all logic circuits will simply be the you'll have 2 outputs. That's what Jonathan's question was. Yeah, can we consider this to be a 2-bit output? The answer is no. It's still a 1-bit output. Q naught is simply the inverse or the opposite of Q. If Q is 0, then Q naught is 1. If Q is 1, then Q naught is 0. That's it. But it's still a single bit output. It only stores 1 bit of information.
And that will be the output.
And that will be Q. Yeah. Q naught is just there. If someone else, if a designer wants to build a circuit with something else, then yes, let's say there might be two LEDs and one red, one green to indicate some status of a machine. If it's green, then red should be off. If red is on, then green should be off. And so you could tie it together. Yes. Right. So not allowed means unpredictable. Not allowed is in the sense when you are designing a circuit, you're not allowed to have both inputs high at the same time. So a circuit designer, if they're a circuit designer or a machine designer, they're trying to design some piece of equipment, then they have to take care to make sure that both inputs cannot be one at the same time, because then the circuit will be unpredictable. The output would be unpredictable. We would not be able to state whether the output Q is 1 or whether it's 0. Depending on which input goes faster. I mean, doesn't matter how synchronous you make it, both inputs going down to the millisecond, microsecond, or nanosecond will never be exactly 0 at this exact same time. So depending on which one was faster, you could get, for 1 fraction of a second, you might have R is 0 and S is 1. And then R is 1 and S is 1. So output might be reset, but it could also go the other way around. So you would not be able to predict what the output is. So not allowed is basically from the perspective of the designer, that the designer should take care that the inputs never go high at the same time. Because the SR flip-flop will become unpredictable. We would not be able to predict what the output would be. Undefined. There are many terms we can use, but unpredictable, undefined, yeah, undefined. And that's why we say not allowed. But again, this clocked SR flip-flop is the same as the SR flip-flop, except we now have an extra input, extra clock input to synchronize the operation of this flip-flop, with some other circuits, with other logic circuits. So if you think about it, right now we're just looking at like a very, very, very small building block. The most complex piece of circuitry would be the PCs, the computers that we use, high-level computers, right? Even the low-level computers like microcontrollers, smaller microprocessors that are like on an individual basis, like a small system, that's very complex. This is like one of the most complex pieces of logic circuitry. So you have your central processing unit, the CPU, the processor. You have your graphics card, which is your GPU. Then you have the memory controller. You have lots of other peripheral controllers. All of those need to be synchronized. And the clock takes care of everything. So you have hundreds of thousands of logic circuits in there. And all of those circuits are synchronized by that clock. And the speed of the clock is the speed of the processor. Basically, how fast the processor can work. So the symbol for a clocked SR flip-flop will have 2 RS inputs, 1 clock, and Q naught at the output. So flip-flops in general have this kind of square shape. This kind of square shape. And that brings us to a clock SR flip-flop with preset and clear. Preset and clear. Now, I won't go too much into detail on the operation, and it gets too complex. We could sit here and talk about it for hours. Every single input, every single combination, trying to find the output. But in summary, what a preset does is exactly the same thing as set. In logic circuits, set means setting the value at 1. Reset means you reset it back to base, which is 0. So set is 1, reset is 0. A preset is basically setting the output at 1 even before any input or clock arrives. So, well, not offset, but it's is you're just setting it pre-arrival of any of the inputs. So set is 1, reset is 0. Preset is basically setting it before or pre-arrival of the inputs of the clock, independent of everything else. So preset will set the output high without any input present. Doesn't matter what the input is, doesn't matter whether clock is present or not. A preset signal will set the will set the output high. Without looking at everything else is exactly the same. Just look at the preset. What happens? What kind of gate is that? Right here, this one, where the output is connected. Sorry. That's an OR gate, right? So if preset goes high, what's the output of that OR gate? 1, right? It's an OR gate plus. So it doesn't matter what the other input is, as long as preset is 1, output Q is always going to be 1. So if preset is 1, output Q will always be high. And that's why it works as a preset. Now, clear CL basically clears out the input. So if Q is equal to 1, Q naught is going to be 0. And if this goes high, then Q naught goes high. And if Q naught is 1, Q goes to 0. So clear does the same thing, but on the other side. So preset means it presets Q as 1. Clear means it clears out the output and sets it to 0. So kind of like how I restarted the computer right now, and I cleared out everything from the memory. It's kind of like that. Clear everything out. And the other part of the circuit is the same SR flip-flop and the clocked SR flip-flop that we saw previously. The symbol remains the same. You have a square indicating the flip-flop. You have inputs R, S, and a clock signal. The outputs Q and Q naught, the inverse of each other. And then in addition, you have a preset and the clear. Preset and the clear. The operation still remains the same. When set goes 1, output Qn goes 1. When R goes 1, Qn goes 0. 1, 1 is still unpredictable, and hence we say it's not allowed. So at the basic, it is still a SR flip-flop with just multiple inputs. Now, the reason we talk about this is because it is not just for SR flip-flop. This is basically present in every logic circuit, right? So the preset, the clear, the clock is there in every digital circuit. This is just explaining it in a very basic level, right? What it means to set, what it means to preset, what it means to clear.
So what was clear?
Clear will set the output to 0. It clears out the memory and sets it to 0. It's like pressing all clear on your calculator. It clears out everything. Yes. So memory is, well, if it's Qn minus 1, it is storing that bit of information, right? No matter what happens, as long as the clock doesn't arrive, it is storing that bit of information. So yeah, we're only talking about 1 bit, but modern computers are 64 bits. So each bit is like 1 line. All of them put together are known as a bus. So previously we had 32-bit, 16-bit processors, 16-bit bus, 32-bit processor, 32-bit bus, 64-bit processor, 64-bit bus, like BUS. And so everything's running in parallel all at the same time. So 64 lines. So you'd have 64 of these. Well, if you were doing some simple circuit 64-bit, then you would have 64 of these flip-flops for each bit. Yes.
So if the clear
So here, and I was going to talk about that in the next few slides, but I'll talk about it now. All of these inputs is basically active high. Active high. Active high means whenever these inputs go to logic high or logic 1. So when clear goes to 1, output Q goes to 0 because output is now being cleared. If preset goes 1, output is preset to 1. If there was a bubble at the end, so if you have something like this, you remember the NOT gate? What does the bubble indicate? Inverter. So if there's a bubble at any of those lines, it means it is active low, meaning when the signal goes to 0 is when it is activated. So if there was a bubble here, we could say, or we could state that when clear goes low, the clear is activated and the output goes low. If there was a bubble here at the preset signal, you would say when the preset goes low, preset is activated and the output will go high. The words preset and clear simply mean preset output is going to go high. When clear is activated, output is going to go low. That's all it means. Active low and active high depends on the circuit designer, on what their needs are and what their purpose is. Yes.
Why in this case it doesn't matter the clock to be 0? I mean, it's not like clock to be 0 is supposed to be
Where?
in the table. Why in this case when the clock is non-zero, it will, I mean, it only gives in case that it's 1 but not the clock is 0.
So you're talking about here? Well, preset and clear operate independently of everything else.
Oh,
They operate independently of the input, they operate independently of the clock. So preset is you want to provide some output before the input arrives, before the clock arrives, before everything else arrives. And so preset and clear work independently of everything. And hence we have a don't care at the clock, don't care at the set inputs, don't care at the R inputs. It doesn't matter what RS and clock values are. If preset goes high, output will remain high. And that is evident by these OR gates right there.
oh yeah, what I'm trying to,
Yeah, go ahead.
the other one is what I'm trying to say is, for example, the preset and the clear is 0 in that case, and you have RS, for example, that
Then it works like a regular flip-flop,
okay,
regular SR flip-flop.
clock is 0 everything.
Yeah. Yeah, then it works like a regular flip-flop. Yes, ma'am. Same question. Okay. Yeah. So if so if preset and clear are both 0, then they are not activated. If they're not activated, then it works like a regular flip-flop. So preset and clear is something that you would do before anything else arrives. If you want to store a predetermined value for the output, that's when you would use preset and clear, right? If you want to preset the output to high or whether you want to set it to low, you would use preset and clear. So independent of the input, independent of the clock. Wow, it's only 4 minutes left. Let's move on to D flip-flop. But before that, let's talk about edge trigger. So we talked about the pulse width, right? Pulse width. Basically, this would be one time period, 1T, right? Sometimes this can cause issues in digital circuits because if the clock pulse width is too wide or the input signal pulse width is too wide, there might be a transition period, like how I was saying, the output could be unpredictable, right? The output could become unpredictable. So to avoid that, we use what is known as an edge trigger. And the edge trigger takes into account just the edge of the clock pulse, not the entire width. The entire width of, let's say, if it's a 1 second time period, then for one entire second, your logic high is going to stay at +5 volts, right? This may cause issues because if one or two of the signals are not synchronized, you may have like a 0 and a 1 or a 1 and a 1 at the same time. So to avoid that, instead of having the activation for the entire length of the time period, we only activate for the transition, the edge trigger, meaning the edge of the waveform. And the edge of the waveform is like this. This is going from 1 to 0. So it is going down in value, right? This edge right here at the end of time period 1 is going down in value. This is going up, going from 0 to 1. This is again going down. This is going up. This is going down. So anytime it transitions from 0 to 1, we say it's going up. So we say it's a rising edge. If it's going down in value, meaning going from high to low, we say it's a falling edge. So rising edge and falling edge. The other commonly associated terms are basically leading edge and trailing edge, positive and negative. We also say positive going transition, negative going transition. But everything has to do with the edge of the pulse width, right? Edge of the pulse, and hence a edge trigger. The circuit is triggered by the edge of the waveform. Okay, so positive edge, negative edge, falling, rising, leading, or trailing. All of the most common words associated with, with these digital signals. One of the places where you would have seen this is on the oscilloscope. If you're taking the lab, and I don't know if you have done it in 361, but in 251, definitely when you did the oscilloscope experiment, you were trying to find the time constant of the waveform. And you were setting the edge either to a rise edge or to a falling edge. Does anyone remember that? You're trying to find the time constant of the charging pulse of the waveform. And so you would set, if this was the waveform, the charging of the capacitor was like this, exponential, discharging was this. So you set the trigger to the rising edge to calculate the charging time constant. And you set the trigger to the falling edge to find the discharging time constant. That's where you had used it. It just basically moves the cursor and attaches it to that place. But anyway, the larger purpose is to basically synchronize all the circuits and to avoid confusion or unpredictable states in the circuit. Okay, unpredictable states. Yes.
So the sensitivity to the triggers, is that going to be on a spec sheet, or is it just
It's spec sheet. It depends on the designer, on how they designed it. Yes. Well, there's lots of considerations when they have to design these kind of circuits. Yeah. Okay, so we'll stop right here. We have, let's see, how many slides do we have left? Yeah, about 8 more slides. So 8 more slides. We'll cover and finish all of them up on Friday. Hopefully in the next week will be computer architecture. And I'll try to get a little bit into MOSFETs, just as a general knowledge kind of thing. All right, so have a good day, and I will see you all on Friday.
So for edge trigger, what does it get from? Just that it has like going up and going down.
Yeah, it just activates at each transition edge. Yeah.